This is a negative of one of the photos. It has markings showing where the star's positions seem to have shifted. Since then, observation after observation have confirmed that matter curves space and slows down time. So the simple question of why things fall the way they do has led us deeper and deeper into the very nature of space and time itself. Gravitational science shows us how galaxies, stars, and planets form. By measuring gravity, we've discovered the existence of dark matter, that 80% of the mass of our universe is invisible, and we don't know what it's made of. And we've detected exotic objects with extreme gravity, like neutron stars, which have more mass than our sun, yet are only 20 kilometers across. But it's another mysterious aspect of Einstein's universe that I want to explore in my next gravity project. Here at the University of Surrey, some colleagues and I have been working on it for months. What we're doing is devising a nationwide citizen science project. We're developing a smartphone app that uses the GPS contained on your phone to explore one of the strangest properties of gravity, how it affects the rate at which we age. I formulated the equations myself, and a small team of computer scientists and software developers is using them to devise the app. Einstein discovered that as gravity changes, so does the rate that time ticks. This means the strength of gravity you feel affects how quickly or slowly you age. The aim of my app is to demonstrate this effect. It works by using a phone's GPS data to estimate your local gravity. And it also calculates the average speed at which you move, because this too affects the rate at which you age. It then uses the equations I've written, which are based on Einstein's theory of relativity, to calculate overall how fast or slowly you're aging. Once the app is ready, I tweet about it. Thousands of people download it, and we start to gather results from across the country. Some people send me videos giving me their results. How fast they're aging compared with how time ticks out in space in zero gravity.
Over the past day, I have aged less by about 172 microseconds.
I have aged less by 10.02 milliseconds. So since downloading the app, I have aged less by 1.14 milliseconds.
Since opening Time Warp, I have aged less by 2.6 milliseconds.
Our aim is to use their results to build up a map of how time flows because of gravity. My smartphone project provides just one insight into the space and time which Einstein's theories describe. Gravity and its strange ways have given us astonishing insights into the dark secrets of our universe. Perhaps the weirdest objects in the universe are black holes, collapsed stars whose gravity is so strong that not even light can escape their grip. Now, for the first time ever, their effects have been felt on Earth, and they've been detected through the medium of gravity itself. It's a story that has revolutionized the study of modern cosmology. 1.3 billion years ago, in a galaxy far, far away, two black holes swirled around each other, drew closer and closer together until they finally collided with incredible violence. In that final fraction of a second, at the precise moment that they merged, a disturbance was created that sent ripples out through the universe. Gravitational waves are a key prediction of Einstein's theory. Matter doesn't just curve space-time, it can cause waves, ripples which expand outwards, exactly like a stone dropped in water. This particular wave was unimaginably large. The energy released was greater than all the light being given out by all the stars in the universe. The wave rippled through space at the speed of light. In 1.3 billion years, it covered a distance of over 10 billion trillion kilometers. Until, on the morning of the 14th of September, 2015, it arrived here. The streets and cafes of New Orleans, in fact, everything in America and on Earth, expanded and contracted very, very slightly as the wave passed through. No one noticed, as by the time it arrived here, the distortion was phenomenally tiny. Except that one science laboratory did notice. And I'm going to see it. 1,000 scientists across the world are collaborating on it. It's the culmination of over 50 years of effort and is one of the most sophisticated experiments ever devised by humanity. So I'm pretty excited to see it. It's a rather unusual setting. Here I am in the middle of rural Louisiana, about an hour's drive outside New Orleans. I don't expect to find such a multi-million-dollar cutting-edge research facility as this. And yet, this is the place where recently one of the most important scientific discoveries in human history was made. This is LIGO. The Laser Interferometer Gravitational Wave Observatory is an enormous construction shaped like an L, with a sophisticated laser system bouncing up and down the two arms.
So we're standing on top of one of LIGO's two arms. This is the first LIGO arm. And in that tube, there's a laser beam that we bounce back and forth between a mirror in the end station and a mirror in this building. And the other bit goes that way, 4 kilometers, perpendicular to the arm we first saw.
This is the L shape.
It's a big L on the ground. So the light bounces back and forth in that arm and bounces back and forth in this arm. And what we actually measure with LIGO is the length of this arm as measured by the light between the two mirrors, and the length of that arm as measured by the light between two mirrors. And then the laser interferometry measures the difference between those two arm lengths.
So as the gravitational wave passed through, the lasers picked it up. They detected that LIGO's two arms changed in length to a very, very tiny degree.
The signal that we saw was just a few thousandth of the size of the atomic nucleus. Is the biggest the signal ever got.
So far, far smaller than the size of a single atom.
Oh, much, much smaller, yeah, that would.
And you need something this huge to pick that up.
That's right. And so this is one of the biggest source of energy in the universe, one of the biggest events you'd ever measure, and we just barely saw it.
The LIGO scientists turned the gravitational waves into sound waves. So what you're about to hear is, in a very real sense, the sound of two black holes colliding.
It was the first observation of any kind of pairs of stellar mass black holes. Stellar mass means, several or a bunch of suns in weight. And so we learned that they exist. We learned that there are enough of them that occasionally they run into each other and coalesce. And we also learned by comparing the waveform we observed with general relativity calculations that general relativity is, as far as we know, dead on right.
The long concrete bunker to my left houses the beamline, one of the LIGO's laser arms. The detail and the effort that's gone into isolating the beam from the outside environment reminds me very much of Cavendish's famous experiment. He too had to worry about isolating his experiment from external disturbances. Only, of course, LIGO takes things to a far, far greater degree. Inside the arm is one of the largest and purest vacuums in the world. Atmospheric pressure in there has been reduced to 1/1,000,000th of the pressure outside. The mirrors inside are so reflective that they only absorb 1 in 3 million photons. And at the end of my little trip lies a British success story. Well, I made it all the way to the end of one of the LIGO arms. To be honest, it took me a bit longer than I thought, especially in that thing. But housed inside this building is one of the reflecting mirrors that bounces the laser beam all the way back down the 4-kilometer arm to the main control center. And the technology that went into developing these mirrors is quite remarkable. It was developed in the UK at the University of Glasgow. This is what the mirror looks like. Its surface is extraordinarily smooth. No bump bigger than a few billionths of a meter high. Equally amazing are these. Fused silica fibers, a few times the thickness of a human hair. Designed by the University of Glasgow in conjunction with scientists from other British universities. They isolate the mirror completely, so it hangs perfectly still. You could say that in there is the quietest place on Earth. Despite this, outside events do sometimes interfere with the work here, as I witnessed for myself. I've wandered into the control room here at LIGO because I'm told something kicked off a few hours ago, and they're all very busy. The image that's flickering up there is not meant to be like that. Essentially what they've picked up is a seismic disturbance, an earthquake. Now that's not an earthquake down the road. It started on the other side of the planet in Japan. So it just gives us a sense of the tremendous challenges faced by LIGO and the team here and the level of sensitivity needed, that an earthquake on the other side of the Earth can disrupt their measurements and have to reset everything all over again. One of the scientists involved in developing this extraordinary place put it quite succinctly. Once we were blind, but now we can see. Throughout the entire history of astronomy, we've studied gravity and how it affects matter in the universe and how it warps space-time, but only by looking at the light that enters our telescopes. Now, for the first time, we can study the universe in a different way. The discovery of gravitational waves means we can see objects that cause extreme warping of space-time and its effect on gravity directly. This essentially opens up a new era in astronomy. It gives us a new way of looking out at the universe. Professor Sheila Rowan was one of the scientists who spearheaded the British effort for LIGO. For her and her colleagues, gravitational wave detection is just in its infancy. New instruments, even more sensitive than LIGO, are now being developed.
There's so much that we don't understand about the universe that we live in, and this has suddenly given us a new tool